Today's my lecture topic is rocket engine systems. Mainly the rocket engine system consists of thrust chambers. The thrust chambers is the combustion device where the liquid propellants are mated, injected, atomized, mixed and burned to form hot gaseous reaction products, which in turn are accelerated and ejected at high velocity. The basic relations governing the determination of the thrust chamber performance, particularly specific impulse and combustion temperature. The parameters such as thrust, flow chamber pressure, throat area are given. The cooling and heat transfer is also discussed in this. A typical rocket thrust chamber assembly consists of the following principal parts. One is nozzle, second one is combustion chamber, injector, mounting provision and an ignition system. That's all. If non-spontaneously ignitable propellants are used, in some cases the thrust chamber assembly also includes integrally mounted propellant valves and controls. The chamber is the third part of the rocket thrust chamber assembly, in which the combustion or burning of propellants takes place at a high pressure. The combustion chamber volume in a liquid propellant rocket thrust chamber is ordinarily selected with the attention of the following consideration. One is the volume has to be adequate to permit adequate mixing, evaporation and complete combustion of propellants. Chamber volumes vary for different propellants with the time delay necessary to vaporize and activate the propellants and with the speed of reaction of the propellant combination. When the chamber volume is too small, combustion will be incomplete and the performance will be poor. With higher chamber pressures or with highly reactive propellants and with injectors which give improved mixing, a smaller chamber volume is easily permissible. For prolonged firing durations, the wall surface area has to be cooled by one of the cooling methods mentioned in the next section. In order to reduce the cooling requirements, it is desirable to decrease the exposed wall surface area and the local heat transfer intensity. As the chamber volume is decreased, the exposed wall surface area is decreased. The average heat transfer intensity is increased because a small chamber volume necessitates high gas velocities. For any given rocket chamber size, geometry and propellant, there will be a chamber volume for which the product of the average heat transfer intensity and the wall surface area is a minimum. Because rockets power airborne vehicles, their weight is at a premium. A small weight dictates a small chamber volume. The weight will be a function of the chamber pressure and the configuration, the minimum wall surface area and therefore the least weight for a given volume are obtained in a spherical shape. Manufacturing and design consideration indicate a preference for a simple chamber geometry such as cylinder or SPR. Various geometrical shapes of a combustion chamber have been used. The maximum chamber diameter often determines various vehicle dimensions. A small unit therefore often permits a lower aerodynamic drag and a smaller structure. The chamber volume and the geometry determine certain acoustic vibration frequencies. Sometimes the chamber volume can be also selected as to avoid the excitation of natural frequencies which may be critical to other components in the vehicle. The gas pressure drop for accelerating the combustion products within the chamber should be minimum. and a reduction in the nozzle inlet pressure will reduce the exhaust velocity and the performance of the vehicle.